In this module, we will look at a demultiplexer. A digital demultiplexer is a logic device which has an input, many outputs and selection lines. Depending on the values in the selection lines, this input is transferred to one of the many outputs. So, as I mentioned, a demultiplexer, as an example here shown, has an input line, 2 to the power of n output lines and n selection lines. Depending on the value on the selection lines, the input is transferred to one of the many outputs, which in this case are 2 to the power of n outputs. Input is transferred to one of the 2 to the power of n outputs depending on the values of the selection lines. So, I could say a demultiplexer is an inverse of a multiplexer. A multiplexer takes many inputs and transfers one of the many inputs to a single output line. A demultiplexer takes an input and transfers its value to one of the many outputs depending on the selection lines. So, let us see how do we build a demultiplexer. An example of a 1:4 demultiplexer has an input, 4 outputs. In order to route the input to one of the 4 outputs, there are 2 selection lines. So, the block diagram of a 1:4 demultiplexer will now have an input, 2 selection lines and 4 outputs. Depending on the values on the selection line, the input is transferred to one of these outputs. So, let us say how do we build it using gates. So, I need 4 outputs. So, I am going to use 4 AND gates whose outputs are the 4 outputs of my demultiplexer. I could call them as O0, 1, 2 and 3. My input line can be called I and my selection lines can be called A and B. So, I want my output O0 equal to input I when my A equal to 0 and B equal to 0. So, I get a function O0 is I dot A bar dot B bar. So, I can pass my A through a NOT gate to get A bar. I can pass my B through a NOT gate to get B bar. So, I can connect my I input directly. I can connect my A bar input as well as B bar input to the 3 inputs of this 3:1 AND gate, and I get my output Y implemented as per this function. On similar lines, I will now write my O1 same as I when my A is 0 and B is 1. So, I could connect I here, A bar here and B here. My output O2 is same as I when my A is a 1 and B is a 0. So, I connect I, A and B bar as my inputs for O2, and my final output 3 is same as I when A is 1 and B is 1. So, I connect I, A and B as inputs for the 4th gate. I will get my output 3 here. So, I am able to transfer the input I to one of these 4 outputs depending on my selection lines A and B is what I call this as a 1:4 demultiplexer. So, let us look at an application of a demultiplexer. Here I have a processor and I want to connect one of the 4 devices to the processor. The devices are a printer, a plotter, a fax machine and a projection system. So, I want the information on the processor to be transferred to one of these 4 lines controlled by the selection lines A and B. So, I say if my A and B both are 0, information on the processor is transferred to the printer, so I am able to print a data. If it is 0, 1, processor information is plotted. I could connect it to a fax machine, I could project the information onto a screen. So I am able to connect a single device to one of the many devices with the help of a demultiplexer, which in a way one of the many devices share a common input line, is what my demultiplexer function is. So let us look at application of a data communication network which is built using a multiplexer and a demultiplexer. So here I have 4 transmitters and 4 receivers. In this case, my transmitters and receivers are essentially computing systems. I am connecting the outputs of each of these transmitters through a single data channel to 4 receivers which are shown here. So what happens in this case is, I am going to connect the outputs of these 4 transmitters through a multiplexer, whose output in turn is connected as an input for the demultiplexer, which are connected to 4 more devices here. So if my S1 and S0 are both 0, 0 at the transmission end as well as at the receiving end, I know now a multiplexer picks my input I1, make it available on the output line, which also is made available as an input for the demultiplexer. Because its input is 0, 0, the same I1 is transferred to the system 1 here. So essentially we are transferring information from the system 1 here through this network to the system 1 here. Same thing I can do for transferring inputs of system 2 to the system 2 by changing the selection line, system 3 to 3 here, 4 to 4 here. But you will find here at any given point of time only a transmitter can transmit data through a common communication channel to a receiver. The way it is transferred depends on the values applied at the selection lines. So I could use a counter whose values could change, for example, from 0, 0 to 0, 1 to 1, 0 to 1, 1. Accordingly, one of the inputs through the channel gets transferred to one of the outputs. So I am able to transfer multiple input information to multiple output devices using a single communication channel. We call this as data routing through a single channel, but it is being shared one at a time, which uses the concept of a time sharing. So I could use a multiplexer and a demultiplexer for a data communication application like this. So a demultiplexer is a device which takes one input transferred to one of the many outputs. A multiplexer is a device which takes many inputs and one of the many inputs are transferred to the output. Both depends on the values on the selection lines.